Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's take a look at our lesson for 4.2.2. This is looking at proportional relationships and how they look in tables and graphs. So it says in lesson 4.2.1, you learned that you can identify proportional relationships by looking for a constant multiplier. In fact, you have already seen the relationship with a constant multiplier in this course. Today, you will revisit the earlier situation that contains a proportional relationship. So remember in that chapter 1, very early on, we learned about the million penny tower, and we were predicting how many centimeters tall that tower would be. And so you were given the task of collecting pennies in your house and measuring how many pennies stacked up to make 1 centimeter. And then we used that piece of information to try and figure out, well, how many pennies would be in 2 centimeters, or 3, or 5, or 10, or 20, or 100, or 1,000. Then we worked in reverse to try and figure out, okay, so if that's the case, how can we figure out how tall a million pennies would be? And you may or may not have thought about it at the time, but that was an example of a proportional relationship. So let's just read this. In chapter 1, you found a multiplicative relationship between the height of the stack of pennies and the number of pennies in the stack. That is, you could always find one piece of information by multiplying the other by a constant number. So here's this table at the right. If you've got the information from chapter 1, you can go in and you can look at some of these figures, but you may recall that there were 7 pennies in 1 centimeter. And so that meant that your multiplier was the number 7, right? What strategies did you use to find the missing numbers? You may recall you either multiplied by 7, right? 1 times 7 is 7. 15 times 7 is 105. Or you could have taken the final number, 63, and divided it by 7, and that would have given you 9. So here's a key question to answer. Let me go ahead and maybe I'll just get rid of these guys so you can see, you can fill that table in completely. How many pennies are in a tower that is 0 centimeters tall? Well, if it's 0 centimeters tall, doesn't that mean that there has to be 0 pennies in that tower, right? So this is where we learn that the whole idea of 0, 0 applies to this situation. Not only is there a constant growth rate, a constant multiplier, but also 0, 0 applies. So we're going to now graph this data. It says be sure to scale the axes so that all of the points in your table are visible on your graph. Okay, so what do we need? It's saying, I don't know that we actually have to go to the 15 and the 105. We absolutely want to be able to include some of these points. So maybe having your graph go up to 12 or at least 10 so that we can fit 1, 2, 3, 4 different ordered pairs, actually 5 if you include the 0, 0. And then you would want, if we're going to make it up to 9 or 10, then you want to make your y-axis up to 63 or 70. So that's what I decided to do. I just tried to get it so that we could get up to about 9, and of course I'm cutting it a little bit short here. So create a graph that looks like this. Your y-axis is going to be representing the number of pennies, and the x-axis should represent the height of the tower. So I would like for you, remember, these are all examples of ordered pairs. So if you take this data right here, 1, 7, that's going to be equivalent to an ordered pair of 1, 7, where x is the height of the tower and y is the number of pennies. And so you would come down to the graph. Stop it. What have I done here? What have I done? So you come down to the graph and you go 1 and 7 is going to be approximately right there. And then we can label that. Okay. So why don't you pause? I'm going to pause and complete that graph based on the information in the table. All right. Hopefully you've got the graph in and you've got these points are in similar places. Now I do want to offer you up a little bit of a tip for graphing. I would recommend that when you graph, that you take the points on your table that you can fit onto your graph, and you take the ones that are farthest away from each other, and you put a line through those points. If you do that, you're going to get the most accurate graph possible because all of these other points should fall right into place. Because you're going to learn that these ordered pairs that you get out of the table correspond to the points that are going to be on your graph, which represent information or what we'll eventually call solutions to rules that pertain to these given situations. So if you plot the ones that are farthest away, then everything in between should fall right into place. Whereas sometimes students will want to graph the first couple of points and connect those dots. And if they're just a little bit off, that means the line is going to be a little bit off as you move farther up. Okay, so just a little bit of a tip. This would be what the graph would look like. Now notice this is the what we would call the unit rate here, because this is where when x is equal to 1, what is y equal to? This is what our multiplier is in this situation. So 3 times 7 was 21, 4 times 7 is 28, 9 times 7 was 63, and so on and so forth. So this particular point where x is equal to 1 is a very important point because this number becomes your unit rate. So let's answer the question. What do you notice about the graph of height and the number of pennies? How does it compare to Sonia's graph of birdseed that we had yesterday? So you can take a look at the graph that you did yesterday and look at it. And what are the similarities? Well, the fact that they're both straight lines and they pass through 0, 0 makes both of those situations, the million penny tower and Sonia's birdseed, proportional in nature. What would be different would be whatever the unit rate is. And so in this case, the steepness of the line is a little bit different. If you recall, I'll just put it on here, even though my labels aren't the same. This was 1 pound was $6.75, and I believe 8 pounds was 54. So that would have been here, somewhere around there. So if we took and graphed that line, let's do this in green, this line would have looked just a little, not much, a little bit less steep than the red line, which represents the million penny tower, or the number of pennies per centimeter on the tower. So something to think about. Proportional relationships, depending on what their unit rate is, will have a different steepness to their line. But otherwise, they'll pass through 0, 0, and they'll be straight lines. Okay, so let's take a look at Casey. Casey loves cheese and buys it whenever she can. She recently bought 5 pounds of mozzarella cheese for $15 and 3 pounds of Havarti cheese for $7.50. So on Classroom, there is a graph, some graph paper for you to use to complete this project. What we're going to do is we're going to put this information into a table, into a couple of tables, one for the mozzarella and one for the Havarti cheese. And then we're going to take that data and we're going to put it on a graph so you can see the comparisons of the two lines. Okay, so let's just go ahead and do that. And so we've got it started right here, and I took the data that was provided within the problem. We know that 5 pounds of mozzarella is $15 and 3 pounds of Havarti is $7.50. We also know that if we don't buy any cheese, we don't spend any money. So that's what makes this a proportional relationship. Now, we're assuming that there's going to be a constant unit rate here because they aren't giving us any information to say if you buy like 10 pounds, you get a discount. So without any of that information, we are going to go ahead and say there's a constant multiplier, a constant unit rate, and it's our job to figure out what the unit rate is. So what I would like for you to do now is fill in this table completely. Find out what the unit rate is. If it's $5 or $15 for 5 pounds, how much is it for 1 pound? If this is $7.50 for 3 pounds, how much will it be for 1 pound? So go ahead and pause and fill in that table. Okay, we ready for the review? So let's go ahead and what was the unit rate? It looks like if you take 15 divided by 5, you're going to get the price for 1 pound. And this is all based on proportional reasoning. Remember, you take the price, $15, and divide it by the unit of weight, in this case is pounds. We're going to find out what the price is for 1 pound. And this is kind of us doing a giant one kind of a process where instead of multiplying something times 5 to get 1, you would divide it. Or I suppose you could say multiply times 1/5. And what is 1/5 of 15? It's the same as 15 divided by 3. So that's what we're doing in this situation is we are taking and dividing by a giant 1 of 3. So that means that our unit rate has to be $3 per pound. Okay, so I'm going to go ahead and write this right here. $3 per pound is the unit rate for mozzarella. So if that's the case, then 2 pounds would have to be $6, 3 would be 9, 4 would be 12, and then of course 5 is 15. That's the information provided in the problem. Now we'll do the same thing over here with Havarti cheese. If it's $7.50 for 3 pounds. Wait, what did I do there? I said 3. I think I was thinking of the Havarti. Hold on for a second. I can't have that be wrong. You guys are probably raising your hands right now saying, wait a minute, problem. And it was a problem. We were dividing by 5 here, weren't we? Okay, now that we got that straightened out, this one, we are going to eventually divide by 3 to get the price. I guess we'll just keep it like that. Of something over 1 pound. What is $7.50 divided by 3? Well, it turns out that is $2.50. So if the unit rate is $2.50 per pound, then 2 pounds would be 2 times $2.50, and 3 pounds we know is $7.50. 4 pounds is going to be twice as much as 2 pounds, so that should be $10. And then 5 times $2.50 is $12.50. Okay, so I'm assuming the directions are after we've completed the tables that we should graph the situation, correct? So let's take each one of these and put them on the same exact graph. So let's start with the mozzarella. I'm going to do this graph in blue because I've color coordinated that. And so everything is already labeled. So the cost of the cheese is the y-axis and the number of pounds is the x-axis. So we know that with mozzarella cheese, 0, 0 absolutely applies. For 1 pound, it was $3. I'm going to go ahead and label that since it's the unit rate. That's an important point. 2 pounds was $6. And then remember what I mentioned earlier about how if you plot the points that are farthest away from each other, 5.15. Where's 5.15 going to go? It's going to be right here. Everything else should fall into place. Let's go ahead and connect those points. And does everything else fall into place? It absolutely does. So there was the 1.3, there's the 2.6, there's the 3.9, there's the 4.12, and so on and so forth. Maybe I'll label this one 3.9 because we want to label like 3 points. All right, so that takes care of mozzarella. Mozzarella, is that how you spell it? Mozzarella, yes. And now let's do the Havarti. And with the Havarti, I am going to plot 0, 0 and 12.50. And then everything else in between. So here's 0, 0. 5 was 12.50, so what is this? This is 10, 11, 12, 12.50 is exactly in the middle here. And now let's go ahead and connect those points. Everything else should fall into place. All right, hold on for a second. Let me move this guy over there. Let me move this guy. Oh, let's go ahead and put the blue here. What was that, 1.3? Right, so now to the green. This is our unit rate, which is $1 and $2.50. and this was a point here, and this was a point here. 3 was $7.50, and then this one up here was 5, $12.50. Okay, so what are we learning about all of this? Can you find any other points that should be on the mozzarella table? Yes, we did that. We labeled them. Can you find any other points on the Havarti? Yes, we did. Should the points on each be connected? Well, this is an interesting concept we'll get into more in 8th grade. Should they be connected? Now, let's get to the nature of these points. If we were saying that this situation, you could only buy 1 pound or 2 pound or 3 pounds or 4 pounds of mozzarella cheese, then buying 1.5 pounds would not be viable. Think of buying gallons of milk at the grocery store. They sell them by gallons. Of course, you got your pints and your half gallons and your quarts and stuff like that. But let's just focus on the gallons themselves. If you buy a gallon of milk, you can either buy 1, 2, 3, or 4, but you can't buy 1.74 gallons of milk at the grocery store. So in that case, you wouldn't want to connect the dots because none of these points in between would even be valid. Now think about buying gasoline at the gas station. You can buy 1 gallon of gas, you can buy 2 gallons, but you can buy any number of gallons. You can buy 7.34 gallons just by pumping it into your car. So in a situation like that, it makes sense to connect the dots because all of these are in play. So I don't know how often you go to the deli section of your grocery stores, but you can literally just buy a chunk of cheese and it can be any weight. Don't just specifically cut them perfectly into 1 pound increments or 2 pound increments. You can go and say, oh, this cheese is $2.75 because it's a little bit less than 1 pound. And so, yeah, that comes into play. So for this particular answer, should the points be connected? And the answer is yes, because you can buy any number of pounds. You can buy any number of pounds. Okay. So there we go. Which one had higher, which one cost more? Just looking at the graph, you can tell the mozzarella cheese was more expensive than the Havarti cheese because the graph is more steep. And then if you look at the unit rates, you say, oh yeah, it's $3 per pound, whereas this one was $2.50 per pound. Okay, so how do the cheeses compare? What is the same and what is different? So the lines are both straight. I got to spell the word straight correctly there. That's not good. There's a T in there. And pass through 0, 0. And mozzarella is different because its graph is steeper. Which cheese is more expensive? Well, we just said that. It's the mozzarella because it is steeper, right? And what is significant about 1y? Well, y in this case, in all of these points, is your unit rate. So with mozzarella, the unit rate was $3 per pound because the y value when x was equal to 1 was 3. And with Havarti, it's $2.50 per pound because the y value when x was equal to 1 is $2.50. All right, so look back at the tables and graphs you created for proportional relationships in previous problems. How can you use a table to decide if a relationship is proportional? And how can you use a graph to decide if a relationship is proportional? Take a second to think about that. I'll go ahead and pause and formulate your ideas. And if you want to wait until I give my reveal before you write them down because you want to make sure you get the right answer, that's fine. I think it's going to be easier for you to answer the graph question than the table question. But go back and look. We talked about it in class, and it's on the video. What are you looking for within the tables, and what are you looking for in the graph to tell whether or not the situation is proportional? All right, I'm going to actually reveal B first because I think that one is one that you guys probably understand. Remember, you know, looking at the graph, if it's proportional because your straight line is going to be there and it's going to pass through 0, 0, the origin. But what is it that you're looking for on the table? Well, you can look at the ratios or look for a constant multiplier. So if you recall, let's come back over and look at the tables for the mozzarella and the Havarti. There's a constant multiplier, right? You multiply 1 times 3, 2 times 3, 3 times 3, 4 times 3, 5 times 3. That's your first indication. The second is if you were to take any two of these ordered pairs, say the 3 over the 9, and compare it to the 5 over the 15. Are those two equivalent to each other? And the answer is yes, because when you simplify both fractions, they both simplify down to 1/3. Also, if you cross multiply, 3 times 15 is 45, and 9 times 5 is 45. If the cross products are equal to each other, then this is proportional in nature. And you can do the same thing here. If you take 2 over 5, is that equivalent to 4 over 10? And the answer is yes. They are equivalent to each other, which makes this proportional in nature. All right, so now 2 more pages to go, 2 more problems. Which tables below shows a proportional relationship, and how can you tell? So please copy down these tables and go through that check. And if you want to, I'm going to plot these points on the graph to prove whether or not they are proportional or not by looking to see if it's a straight line that you get by plotting this data, or if it is not a straight line, it can't be proportional, right? If it doesn't pass through the origin 0, 0, it's not proportional either. So go ahead and analyze these 2 tables. If you want to create graphs to check it that way, you can do that as well. All right, so what did you get for your answer? Does table A appear to be proportional? Well, does it look like there's a constant multiplier? 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. Yes, it does. The unit rate and the multiplier is 2, and when you graph these points, it's a straight line that passes through 0, 0. So yes, that is absolutely proportional. And then you can see the graph right here. Is there a constant multiplier? 1 times 2 is 2, but 2 times 2 is 4, so there's no constant multiplier there that would work. And if you took 2 ratios from this table, they would not be equivalent to each other, so it's not proportional. And then you look at the graph, and while there does appear to be a constant growth rate, it is not based on the unit rate, and it does not pass through 0, 0. It passes through 0, 1. So this is non-proportional. All right, so these last 4 graphs are not proportional. And your task is to look at each one of them to determine why they are or why they are not proportional. So go ahead and pause. We'll do A and B. You don't have to necessarily copy these graphs into your journal, but if you want to, you can. They are in the online book, and you can see them on there as well. But just looking at them, what makes this one non-proportional? What makes this non-proportional? Okay. Pause for a second, and then when you are ready for me to reveal, I will reveal it for you. So what do all proportional relationships have in common? Well, they have a straight line, correct? And they pass through 0, 0, and this doesn't either. So this is so non-proportional on both fronts. But with graph B, it at least is a straight line. The only issue we have here is the fact that it does not pass through the origin. It does not pass through 0, 0. Now take a look at these and pause. You feel like you've got an idea, unpause. You still paused? Can you hear me talking right now? Of course, you can only hear me talking if you've unpaused. So what is it about this? Straight line is great. We love straight lines for proportional relationships, but it's got to also pass through the origin, and it doesn't. So this is non-proportional. And then this starts at the origin, but is that a straight line? No, this is actually a classic line for what we call exponential growth. It is not linear growth, so it does not have a constant growth rate, but it's not a straight line, and therefore not a proportional relationship. All right, so now we're 2 lessons into proportional relationships, and we're just going to keep practicing this over and over. It's going to keep coming up in our homework on a regular basis, and we're going to find it slipping into later lessons when we're learning about probability, and we're learning about percent problems and percent increases and how simple interest works and how the distance formula works. Much of the math that we're going to be doing for the remainder of the year is going to involve proportional reasoning. So now you have kind of a basic idea of what you're looking at within tables and what you're looking at with graphs. And we'll just have to get deeper into what we're looking for when we're looking at word problems to determine whether or not the situation is proportional or not. And then we will use strategies to solve those problems once we realize that they are proportional. All right, so let's move on to the next activity. Take care. Bye.
Hey, feeling good.